submitted any of the questions in the form, right? I'll be going through those later, so you don't have to worry about that. Apart from that, let's just begin with a short introduction to like naming and all that. So let's start with naming, of course, because that's the first thing you need to know. Because a lot of questions will just give you the name of the compound without anything else. So for naming, all you have to remember is that you take note of the suffix with the highest priority, and then every other group in the molecule will become a prefix. And for nitrogen groups, right, let's say you have something like this, so two methyl groups and a random R group. This will be labeled as N dimethyl something, whatever the R group makes it. Like it's probably some kind of amine in this case. But yeah, that's just the main thing to take note of. And for naming, right, the best way to improve is to practice. And for your suffix functional group, right, the one with the highest priority, there's a priority list that should be in the lecture notes. If you don't have the priority list in lecture notes, you can just drop me a message after this. I'll send it to the H2 chemistry chat. But anyway, just take note of that. And with that, right, let's just start with a few practice questions so that you guys have a rough idea of how much you know. So, try name these two molecules. Once you're done, right, you can just send it to me via DM or something, and I'll tell you whether that's correct. So this is molecule number 1, and this is molecule number 2. Give yourselves 2 minutes to do this. Okay. That's a double bonded to an O. Nice, yeah. Take 2 minutes to do this, and I'll go through this. You can also just directly send me a message with your answer once you're done. Alright, that should be enough time. I'll just go through this now. I'll try to make my voice a bit more interesting so it's less boring, but anyway, let's start off with the first one. So in this case, right, we clearly know that we have one amino group and one aldehyde group over here. Now, generally, right, for priority groups, let's say you just forget the exam, generally what happens is that your C double bond O groups are, for the most part, higher priority than your single bond O or single bond N groups. So in this case, we know that our aldehyde is a higher priority than NH2. So we know that the suffix for aldehyde is like Al, so like L, so like it'll be like, in this case we have 4 carbons, right? So our base molecule will be like a butanol. But then we also have an amine group at our third carbon, because like we take the first one with priority to this, so we have 1, 2, 3. We have an amine group at the third carbon, and the prefix for an amine group is the amino group. So this would just basically be 3-amino butanol. Alright? And the next one, right? In this case, we have both an aldehyde and a carboxylic acid group. Now, carboxylic acid groups are basically the highest priority group there is. So obviously, this has to be our suffix. And one thing I want you guys to remember when naming molecules is that your carboxylic acid groups always have to be at the ends. So if you're saying something like 2-carboxylic acid, or okay, not 2-carboxylic, like whatever the prefix is, right? Then something's probably wrong, so you should check that. That's something to take note of. But anyway, since we have a carboxyl aldehyde group, we know that a carboxyl group is higher priority, so it's going to be something oic acid. This has 4 carbons, so it's going to be a butanoic acid. And then we also have an aldehyde group on the 4th carbon, so we have to call it 4-oxobutanoic acid. So yeah, then the prefix for your aldehydes are bit, which is why I chose this question. So you guys might want to revise that again. So do you guys get the answer for both of these? You can always just like either speak out or just type a yes or no in the chat. Like, just please don't be afraid about speaking. Like, I'm not gonna like flip out or something, but yeah. I just want to check. Like, do you guys swear you get this? Anyone? Please? No. Which one did you not get it? just to check. Like, which one do you have difficulty with? One or two? The oxo, yeah. Let's say it might be good to just like revise that for a few minutes, because like some of them, like the oxo ones, are a bit strange in terms of the prefix. Like the other strange ones, I just refer to my own notes for a second. Okay, cyan is I think oxo is the main strange one, and also like your iodo and stuff, or your alkoxy. Yeah, a lot of people tend to forget the alkoxy one too, which is for your OR group. But anyway, let's move on to the next thing. Yay. Okay. First, talk a bit about half and like full reaction. I covered this in my last lecture as well, which is like actually quite good. So you guys should check that out if you're confused about how reactions work for organic chem. But let's say we have two types of arrows. We have a half arrow and a full arrow. You just need to take note that this is a movement of 1 E minus, this is a movement of 2 minus, and you should always have two half arrows at the same time, at least for H2 chem. Like you shouldn't be moving only one electron in that sense. Even for radical reactions, right? Let's say you have a Cl radical and a CH3 radical. You don't have to like draw two half arrows to connect this. Just for an example, this is like a termination step. Alright, so that's pretty much it for radicals. Now, you guys show us a little about the degree of substitution. Like this is a very simple concept, so I'll just give you guys a simple example with alcohols, and we'll move on to that. So, this is a first degree alcohol. This is a second degree alcohol. I'm just gonna use like R prime. So R prime just denotes like it's different functional groups. So like R prime and R just denote two different like R groups, which is why they are like they have the prime thing. So R prime. This is a third degree functional group. So these are 1, 2, and 3 degree, right? Or third degree, right? So what degree function? What degree alcohol is this? You just type your answer in the chat. Like what degree alcohol is that? What degree alcohol is that? Just type it out. I want to see what you guys type. The one on the absolute left with 3 hydrogens. I mean, that's just a scam question because it's not any degree alcohol, it's just methanol. Just take note of that. Don't be confused by this. Like, remember that for your first primary alcohols, right, your first degree alcohols, you always have to have at least one R group. Alright? And one additional thing you guys need to take note of, like for most functional groups like alcohols and stuff, you'll end up at like third degree max, I guess. You have like tertiary like halogen alkanes as well. But for nitrogen, something interesting happens because it can form a quaternary ammonium salt. So you can have something like this. With a plus charge here. So this is a 4th degree amine. Or a quaternary ammonium salt in that sense. That's something to just take note of. Remember the definitions for an electrophile and nucleophile. Like, don't get confused. The way I remember it, right, is that an electrophile is an electron-loving species. Like, it's the way it's taught in school, basically. So to remember that it's going to have to be electron deficient. In order for it to like electrons, it needs to be electron deficient. If not, it will just get repelled away. Then the same thing applies for a nucleophile. In order to like the nucleus, which is positively charged, it has to be electron-rich. So yeah. Let's say electron deficient or electron rich and donates or that sort of thing. And for free radicals, it's just something with an unpaired electron. Really broad definition, so not much to worry about there. And of course, there's a different types of reactions you need to know. Do you guys want to like list out the different types of reactions just as a type of revision for you guys? Or do you guys want to skip this? I just quickly say 1 to list out the reactions and 2 to skip. I quickly just type something out. Now the main students, so like I'll rather like pick stuff that you guys want to go through. So if you want to list out the different types of reactions that you label, just type 1. If you want to skip that, type 2. Okay, 1. Anyone else? If not, I'll just list out. Okay. Let's go through this relatively quickly. So let's just start off with electrophilic addition. So electrophilic. Oh my gosh. Okay. I need to be careful about spelling. So I'll be extremely careful with spelling too. So remember electrophilic only has 1 L. I don't know if Cambridge is gonna mark it down for crappy spelling, but that's not it. So like this happens in alkenes. So yeah. Electrophilic addition for alkenes. So this basically like an example of this would be your C double, like your ethyl group, let's just say ethene reacting with HBr to form your halogenoalkane. So yay, we have formed the, what, why has this stopped? Oh, are you serious? Icon crashed again. Oh my gosh, okay. Very nice. Okay, nice, my icon crashed. That's fantastic. Give me a few seconds to restart this, and until then, right? Can you guys do a question? Can you guys just like, okay, hold on. Let's just take a break first. I'll be back in 2 minutes. Okay, that was unexpected. Yeah. While waiting, right? You guys can also just think of any questions you might have for today's lesson on organic chem and just type it out in the chat. I'll go through it later. I know someone specifically asked me about doing the application questions, so I'll definitely be doing like a question on that from one of the past year A-level papers, like on the harder ones. Okay. Can you guys hear me? Just to check to make sure everything's working. Can you guys hear me? All right, great. I'm very sorry about the disconnection. Technology has issues sometimes. Yeah, this just shares the screen. Okay, fantastic. So yeah, we were going through electrophilic addition just now. And okay, everything can be seen. Very nice and dandy. So next one will be after electrophilic addition, we also have neutrophilic addition. So both of these are classified as addition reactions. Generally, for most questions, right, when I ask you to like say what type of reaction this is, you have to go for the slightly more specific one. But just read the question phrasing carefully. So, yeah, so if electrophilic addition, so this basically happens in aldehydes and ketones, basically anything with a carbonyl double bond group that's reactive. The reason why you don't see like nucleophilic addition reactions in esters and amides, even though they have those same groups, right, like the same carbonyl group, is because of resonance, like the resonance and like some of the partial positive charge being reduced in that sense. So it's like less electron diffusion. Because when you have resonance stabilization from the OR group or the amide, like the N, like the nitrogen lone pair, right? You basically have more electron density than expected on the partially positive carbon, which causes it to be less reactive. So plus HCN will just lead to you forming your cyanohydrin. So yeah, I don't care chemicals. So after that, we have substitution reactions. So those are addition reactions. Now we're moving to substitution reactions. So the most first one is FRS. Remember to say this out in full. This happens in alkanes, and it's basically like governed by CH4 plus CO2 turning into UV light, and then there you go. Now, yeah, they teach us that FRS only happens in alkanes for like H2 Chem, right? In that sense, but it can actually happen in a lot of things. So just keep that in mind. Like, if you ever see a question where it's like ask you to suggest how this like weird product formed, like give a radical mechanism, don't be like shocked because radical mechanisms happen in a lot of things, especially for high like your peroxide reactions. So yeah, moving on. Electrophilic substitution arenes. So they call it electrophilic aromatic substitution, so EAS. You're just taking this plus your benzene ring and forming. I probably shouldn't have changed my benzene ring, but yeah, forming this. That's HCl. So there you go, that's EAS. Then you have nucleophilic sub. So for nucleophilic sub, you have two types to remember. You have SN1 and SN2, and for our syllabus, it's mostly just for halogen alkanes, but you can also think of it for. It also happens for stuff like replacing your hydroxy groups to, like your halogen groups. So like normally we think about converting like an RX to like ROH, right? But the reverse also happens. Like the reverse process also happens using some form of nucleophilic substitution. The only thing that's changing is that you have to turn this into a better leaving group first. Just something to take note of. The nucleophilic substitution should be quite simple. Just taking a nucleophile and kicking something out from an aliphatic chain to form this. Wow. Okay, next type of reaction goes to elimination. So for elimination, you just have to you have to kick two things out to form an alkene. So I mean, there's more than just an alkene being formed, of course, but I'll just give an example of an alkene. So let's say we have an alcohol group. If you add like your conc HCl stuff, like your conc H2SO4 and stuff, which favors like elimination, you will form an alkene. Of course, you need to like have an acidic solution and all that. Next, you have hydrolysis. So hydrolysis is basically used to describe something that involves like water being used to break a bond in a molecule. So an example of a hydrolysis reaction would just be like your ester hydrolysis back to a carboxylic acid. It's like one of the reactions you done for hydrolysis and like H2 or your amide hydrolysis and stuff. So H2O and heat and H plus. So I'm gonna write down the pros, but yeah. For condensation, right? Usually what happens is that you have two molecules reacting together to form a bigger molecule with the elimination of small molecules like water or HCl. Now something else that you can take note of for this, right, is your degree of unsaturation. So you know how like for your deduction of like structures or your elucidation of structures, you guys know how like whenever you get like a high carbon to hydrogen ratio of 1:1, they say that oh you have a benzene ring, right? Well that's like based off of the concept of degree of unsaturation. Can you just check, right? How many of you know what the degree of unsaturation is? And how many of you were taught? Like if you know what it is, right, just type a 1, and if you don't know, type a 2. So you guys were explicitly taught it in school. So you know how like double bonds reduce like the DOU, increase the degree of unsaturation by 1 and stuff. Okay, that's great. So yeah, just make use of that. Like for a condensation reaction, right, one way to double check your answer would be to like check the degree of unsaturation. But most of the time it's not necessary. Like for chem, it's important to make sure that you guys don't waste too much time on like being stuck and checking your answers. So only check answers like for questions like condensation, like your 1 mark questions and stuff, right? That should be correct if you have time. I would say it's more important to nail your elucidation and all that first, because those are where the marks really said like if you have a 10 mark elucidation question, you should try and get like 9 or 10 for it. So this is an example of condensation. Left oxidation, right? Oxidation has 4 like oxidation reduction reactions are usually in conjunction, so we call them redox, but they can happen separate as well. You just need to remember the 4 definitions, which involves like the addition or removal of oxygen, the removal or addition of hydrogen, the loss or gain of electrons, and the increase in oxidation number or decrease in oxidation number. Let's remember that oxidation is an increase in the number of oxygen, so like an addition of oxygen, but is the removal of hydrogen. Just something to keep in mind. It can be a bit confusing sometimes. But yeah. We will remember that reduction is the gain in hydrogen, by the way, so think about like your alkenes being reduced to alkanes. So what happens? You're adding hydrogens to it. That's just how I remember it, but you guys can have your own methods, I'm sure. So next one is rearrangement. So rearrangement reactions are just the migration of an atom or groups of atoms from one site to another within the same molecule. The most common ones I would consider are like alkyl and hydride shifts, but they're not really taught in like H2 Chem. We don't really learn that many rearrangement reactions in H2 Chem. Actually, we learn any, but yeah. So like just keep that in mind. In case it's tested, like they could just show you an example of like my rearrangement reaction. So let me just give you guys an example. So let's say like Cambridge asks you to ask you like what type of reaction this is. Let's say we have this. They ask you what type of reaction this is. Clearly nothing else is changing apart from the fact that the double bond then still have moved position, so you just call this a rearrangement reaction. There you go, fantastic. Okay, moving on. So for isomerism, right, there's a few types, but the one I want to focus on today is stereoisomerism. Because, okay, I just want to check, right, do you guys want me to go into enantiomerism? Because, like, for some students, it's really, like, confusing, and for other people, they just get it off right off the bat. So, do you guys want me to cover, like, your enantiomerism? I'll just press 1 if you want me to, or 2 if you want me to skip. Okay, if you want to cover enantiomerism, right, if you guys don't understand what's going on, is it because you can't visualize what's happening, or is it something else? Like, what problems do you guys have in enantiomerism? If you guys can specify what you think your issues will help. If you don't know what the problem is, I'll just go through it anyway to try and give you guys a few tips. Anyone, do you guys know what your issues with enantiomerism are? Okay, first let me just clarify something. I feel like a few of you might get this part wrong. So like, what you need to take note of, right, is that for a molecule to be chiral, the only requirement is for there to not be a plane of symmetry. Even if you have chiral centers, right, a molecule may not necessarily be chiral, but as long as you don't have a plane of symmetry, a molecule will always be chiral. The reason why these two things are lumped together is that most of the time, right, for the molecules we encounter in H2 Chem, whenever there isn't a plane of symmetry, we usually notice some kind of chiral carbon. But just remember that not having a plane of symmetry is like the most important. And to like illustrate the example, right, have you guys heard of amines? So this thing, okay, do you guys think this is chiral or not chiral? Do you guys think this has enantiomers? Chiral or not chiral? What do you guys think? Okay, so far two people think it's not chiral. But yeah, it's chiral. It's actually chiral. So this is a classical scam question where they make you think there's a plane of symmetry, but actually isn't. And the way to think about this is that if you have two consecutive double bonds, do you guys think that they can be in the same plane? Just think about it for a second. We know that whenever there's a double bond, right, there's a pi electron cloud below and above the bond. So do you guys think that they'll be in the same plane? If there's two consecutive double bonds. What do you guys think? Like for once they say not curl. Like you think about it that way, because like yeah, exactly. And do you know why XJJ, can you like explain why that doesn't happen? Like there's a reason why we don't see two consecutive like pi electron clouds on the same plane, right? Like the answer lies in something to do with electrons. So like can you just tell everyone what it is? Yeah, JBD is correct. So we don't have too much repulsion. So what happens for this case, right, is that one of your, let's just say that this is one plane, right? So the Cl and Cl right here. The second double bond, right? If you look at it from a side view, right? So let's say I'm looking at it from this plane. So I'm looking at head on. So this is flat and these two things are flat for me. But for the other one, right, one of them will be going into the plane, another one will be coming out of the plane for the other side. So electron clouds are actually perpendicular to each other. So can you guys visualize this? And so what you can do is like hold out your left hand and make it parallel to your computer screen, and then make your other hand perpendicular to your left hand. So if you look at it that way, right, you see that one of the double bonds or your palms is parallel to the screen and the other one is perpendicular to it. So this is what's happening for airlines. And because these two things are like perpendicular to each other, right, there's no plane of symmetry along the molecule, which causes it to be chiral. And something really important, right, is that I can't honestly like spend a lot of time on this now, but you see this like wedge and dash bonds. Like these are really important for you to like practice and stuff. Like just look at a bunch of molecules online and try to visualize them. And a really good resource for it would be something called moleview.org. So what you guys can do is just like go to your browsers, type in moleview, so MOL. I'll just in the chat. So like moleview.org. This thing, oh my gosh, okay. I'm not sure what the website was. Yeah, it's just moleview.org. You guys can just go to moleview.org, right? And mess around with a few of the structures. So just like take some random chiral molecule that like let's just say something like a carbon atom with CH3 group, a hydrogen, a bromine, and a chlorine, and just mess around with it. Yeah, there you go. You guys can take a look at this after the lesson. It's actually really helpful for visualizing stuff if you can't. You can also like type in an example of the airlines of an airline and then just see what the electron clouds look like to get a better idea. So moving on. Oh my gosh, okay. Let us talk about drawing your chiral molecules. So let's say we have this molecule over here. So generally, as long as just make sure that your two groups are of a wedge and dash groups, right, are next to each other, and the other two groups are next to each other. So you can think of it like you can form two V's with your fingers and put them on top of each other. Okay, I can. I'll just turn on my webcam for a bit. So okay, so let's say you have two fingers like this, right? There are two groups like this, which is why you want to draw the two groups next to each other. So that's just it. You guys can just form two V shapes with your fingers and try and form a tetrahedral structure using that. But anyway, going back to this, right? I haven't drawn my last group yet. So let's just say this is a CH3 group. If I were to draw a mirror plane here, this is a chiral. This is like we mark a chiral this with asterisk. If I just draw a mirror plane here, right? I'll be reflecting everything for what it is basically. So we have an OH group here. We have our CH3 group here. We have our Cl group here, and we have a H group here. Now at first, right, this looks like all the bonds. It looks like all the bonds are in the same place, right? What you have to remember is that your molecule on the right, because it's on a mirror plane, is actually rotated compared to the molecule on the left. So it's rotated back such that your OH group is on the right again. So if you were to do that, right, you'll notice that the group's actually in a different location. So you can't really put them on top of each other anymore. Because what happens is that your OH group will be sticking out, now your CH3 group will be behind. So yeah, you guys can, I highly recommend trying it out on MoView. So you see what I mean, right? Is that if you were to rotate this to the right, like rotate the one on the right until it's facing the same thing again, you get something like this. So you get your H values remain on top, but now you bring your Cl back to the side. And what happens now is that your original OH group will now be will now be in front of the plane. So this will be in front of the plane, or this will be behind the plane, which is why it's not the same. We can't stack them on top of each other. So that's something to take note of. Moving on. I mean, do you guys get enantiomerism for the most part? Like, I can't really explain it unless like I can tell what your problem is. So can you guys just like type in the chat like what you struggle with for enantiomerism specifically? Like as long as you follow the steps of like drawing the first molecule on the left, right? Like drawing this on the left and then just following it on a mirror plane, you should be able to get it. And remember that whenever you have two chiral centers, right? You have to draw the 3D structures for both of them. So whenever you have diastereomers with like two chiral centers, remember to draw both of them in the mirror plane. Does that make sense? Honestly, zero chem is all about practice. I used to suck at it too, and I still do for some questions, but if the more you practice, right, the better you get at it. I mean, let's do a practice question on chiral centers. And if you guys don't understand stereochem, right, or some parts of it, please just type it in the chat. Because, like, I need to know what you guys don't understand. Is that okay? But while thinking about that, here's a question for you guys to do. So I'm going to draw a molecule. It's going to be quite big. And all you guys need to do is, like, identify every single chiral center here and mark it out with an asterisk. This. It should be connected. Okay, so just take some time to mark out the chiral centers for this molecule and tell me what the maximum possible number of stereoisomers are for this. How many stereoisomers can this have? So common number of chiral centers. So send your number of chiral centers and send in your number of maximum stereoisomers. So yeah, you guys have 2 minutes to do this. You can just type out your number. You can just type out your chiral centers, comma your number of maximum stereoisomers in the chat. Okay, so 3 chiral centers, and how many stereoisomers are possible? 3, 8, correct. Okay, now I'll just make one simple change to this molecule. I'll just make one simple change to this molecule. How many stereoisomers are there now? Like, what's the maximum number of stereoisomers now after making that one change? Correct. So what I was trying to teach you guys in this example is that whenever your alkenes are terminal, you don't really have cis-trans isomerism. So in such cases, right, your double bond doesn't count towards like your maximum number of stereoisomers. So if you guys don't know the formula, it's just basically 2 to the power of x plus y, which is like your number of chiral centers plus the number of like double bonds you have, or like your restriction for rotation. So like your y, right, which is normally for the number of the bonds, can also apply to rings. And remember that if you have a ring like this, right, if a ring like this with restricted like rotation, let's say you have Cl and Cl, you know your Cl can different planes. So like for this, obviously you can have multiple stereoisomers, but your maximum will just be 2 to the power of n. So this will be 2. Because you can either have like your Cls in the same plane, or you can have them on opposite planes. And even though you can have both of your chlorines like up or down, right, they're basically the same thing. So that's why it's only counted as 1. And if I added a double bond to this, right, the number of stereoisomers wouldn't change. I still have like 2, but if I have something like 1, 2, 3, 4, 5, 6, 7, 8, 8 is a magical number where your thing can like actually have cis trans within a ring. And if you guys look up the shape online, it's kind of cool. But yeah, just something to take note of. Once you have 8 carbons, you can have cis trans about within the ring as well. So your ring can actually fold over itself to form a 8 figure basically. You guys can look at the picture online, it looks quite kind of cool actually. But yeah, that's pretty much it. And for methyl compounds, right, it's basically something that has more than one chiral center but has a plane of symmetry. So what happens is that, let's just see if something like 2,3-dibromobutane. Okay, then maybe I'll draw it out. Let's say if something like this. Now this has two chiral carbons, right? So these two chiral carbons are like chiral, correct? So your maximum possible number of stereoisomers for this is 2 to the power of 4, 2 to the power of 3. And 2 to the power of 2, what am I saying? There's four stereoisomers that's like the max number. But in this case, like how many stereoisomers does this molecule actually have? And the maximum possible we know is 2 to the power of n, which is 4. But how many can this molecule actually have? And what's the actual number of stereoisomers that this has? 3, yeah. And that's because for one of the isomers, right, it's like their mirror image is identical. And because of that, you get a methyl compound. So if you don't know what I'm talking about, just draw it out. Okay, so let's see. So this is I'm drawing this from like the middle carbon. So with respect to like your second and third carbons, right? You can basically have two CH3 groups like this. Okay, then this is your second C. Another CH3 group here. You have Br and H. Now, even if I drew the mirror image of this, right? CH3 here. Oh yeah, one more thing. This notation is okay. You can draw a bond to the hydrogen for alkyl groups because it's obvious that the bond will be to the C. But let's say if something like a COOH, you have to draw your C bond to the C itself and not to like the H or something. Because for cases with multiple atoms that can have more than one bond, it can be a bit ambiguous. That's something to take note of. Here. And there's a Br here. We go Br and H. Now, we already have a problem here because we look at this molecule carefully, right? We realize that there's a plane of symmetry about this axis. And we know that in order for a molecule to be chiral, like you can't have a plane of symmetry. Like the only condition for chirality is not having a plane of symmetry. And because this has a plane of symmetry, right, is chiral. So even though we have two enantiomers in that sense, like forming from this like set of like stereoisomers, right? Because we only picked like one from this because the second one and the first one are identical. Like both enantiomers are the same because it's a plane of symmetry. So you have to subtract one away from the total number of like the maximum of stereoisomers possible. So that's pretty much it for like your basic like introduction to organic chem stuff that's applicable to every sort of question in that sense. So this is like the basics they have to apply to every future topic in organic chem. For the next few like functional groups and stuff, right, what do you guys want to cover? Because we only have like about an hour left. And I said to go through that question about the application questions from that one person. So what topics do you guys want to cover? Like any reactions, anything, that's fine with me. Just tell me like what topic it is and what you want to cover from it. Because it took a lot longer to explain as I expected. So yeah. Just type it in the chat. Like if there's a part of like if there's something specific in organic chem that I struggle with, right? You just type it out. And I'll try and go through that. Okay, nitrogen compounds. Okay, nitrogen compounds are paints. I understand why you would pick that. You can just tell me like what specific reactions from there that you want me to go through. Okay, anyone else apart from nitrogen compounds? I can probably do up to 3 things. So if another 2 of you have anything to go through, right, you can just let me know. And one more thing, right, I'll be doing like one-on-one consultations after this because this will probably be the last lesson. So if you want to sign up for that, just stay tuned. I'll just go through anything you want me to go through for about half an hour to an hour for like a start on the weekend. But anyway, apart from nitrogen compounds, is there anything else? Anyone? You can legit ask me about anything in organic chem, and if I can answer it, I'll try my best to. Like, answer it, of course. And if you're worried about mechanisms, right, you can just look at the previous lesson, or you can just like drop me a message. I can go through pretty much any mechanism in the H2 Chem syllabus. Anyone? Okay, Mr. NTUC, nice username. What part of nitrogen compounds do you want me to go through? the reactions. So like, do you just want to like list them all, or do you want to like go through them and explain why they happen in that sense? Like, what part of the reactions are you confused about? Okay, sure. So like, you guys can take a 2 minute break now because like the lesson has been quite dry so far. I'll start again at 10:48, and if you have any more questions, you can just leave them in the chat, or if you're too shy, you can just like DM me. Like, just send me a direct message on Discord. Okay? So starting at 10:48, you guys can take a break now. BRB. Okay, you guys ready? So I'll just go through like some of the logic behind some of the reactions. So let's start with amines. So as you guys probably know, right? Amines basically have a functional group of, or have the structure of CH2, CH3, and a NH2 group. So this is the amine functional group over here. The first reaction can take place is an acid-base reaction because amines are basic. And remember, like in the previous lecture, I mentioned that basicity is basically the ability of a molecule to like donate a pair of electrons to a hydrogen. So the result of this reaction will just be NH3 plus Cl minus. So these are acid-base reactions. Now, it's kind of strange to see like a plus on like a final product, right? But just trying to use that because like in some ways, a lot of the reactions like your coating ammonium salts happen because of the lone pair being donatable really easily. So it's sort of like a H3O plus, but in this case, like because there's only okay, the reason why like you don't see like H4O plus, right? Is because like once you already have H4O2 plus in that sense, is because like once you already have like one single positive charge on a molecule, it's very hard to get a second one. The molecule becomes like extremely unstable. But in this case, you can still pull off having one positive charge, which allows you to like grab onto a proton or another alkyl chain. So, yeah, okay, so that's the first reaction. And then your second reaction is basically with this. So you can do a nucleophilic sub. So remember your conditions is just CO2 plus heating, and you get something like this. Now, I'm going to focus in on this a bit more. I'm going to talk about how you change like the concentration of the various reactants affects like what product you get. Now, you guys know how like as long as you have a hydrogen on or lone pair left on your nitrogen, right, you can keep on substituting things out. You guys know that, right? So like you can have like you can go from like a primary amine all the way to a quaternary ammonium salt. Correct? So the question to ask yourself is that, let's say I have a primary amine, like let's say I have something like, I start with something like RNH2, and I want to convert it to RNHR prime. Now, if I use something that's like RBR, right, like R prime BR, how do I ensure that this will only it will only replace one hydrogen instead of like all of them? And that's why it's like taking note like the controlling like the relative concentrations of each reactant. So if I do a reaction with RNH2 and excess R prime Br, what do you guys think will happen if we use excess of the halogen alkane? Yeah, so you get multiple substitution. And why does this happen? Let's think about it. So let's just start off with RNH2 and let's do our first sub. So they can have a nucleophilic substitution with your first RBr. You just kick this out, kick out a bromine, and I'll just do a minus H plus at the same time. So don't do this in exam, but I'm just skipping steps here to make things go about a bit faster. You get this, and you have this, and you have the R prime. You also have a H plus, but I removed it. So let's just say a Br accepted the H plus or something else in the molecule to H plus. So that's the first thing, right? Then is that the nitrogen still has a lone pair available for donation. So all it's gonna do is it's gonna just go and do the same thing again. It's just gonna go and attack an RBr again, R prime Br again, and then keep on doing this, and that happens because your RBr is in excess. So like your amine won't stop reacting because there's like more of the RBr than the amine, so they just keep on reacting until they can't. In this case, your amine is your limiting reagent. You just keep on doing this, and then you get, oh no, another substitution. And now you have this. But then that can get substituted again to form your quaternary ammonium salt. So because your amines are the limiting reagent here, right, you have an excess of your halogen alkane to react with, which causes it to have multiple substitutions. But if I were to change the concentrations, right, and say that I have limiting RBr instead, like limiting R prime Br instead, the story is completely different. So instead of getting multiple substitutions like we did just now, what's just going to happen is that if something like this, you're just going to do one substitution and form your secondary ammonium salt. Because it's competing with many other amine molecules to react with the RBr. So that's why you stop at a single substitution. So you have to be very careful about what you're writing for your reagents and conditions. You have to specify that you're saying putting this in a limiting amount or in an excess amount based on what your final product is. Does that make sense? Do you guys understand why that happens now? Like, just type a yes or no in the chat. Like, if you guys do understand why that happens now, right? Okay, that's good. So let's move on. Actually, this isn't like any like reaction in particular because there's like a lot of things in nitrogen compounds, right? And if as you know, a lot of them are repeated. Well, actually, let me just go through the phenylamine thing as well, and you can just write down the specific reactions that you had in mind. So let's think about phenylamine because it's a pretty interesting example that to think about. So normally we say that amines are really good, decent bases, right? In this case, right, phenylamine is a weaker base than your normal amines, right? Do you guys know why it's a weaker base? Have you guys tried to visualize what's going on? Okay, that's correct. So when can delocalization occur? There is an overlap of orbitals, right? So if I have something like this, Now, I'll just give you guys a bit of context. For aromatic things, like for something to be aromatic needs to be 4n plus 2 pi electrons present. So if I have something like this, oh no, I did the wrong one. So this is a heterocyclic ring. They are not usually tested in H2, but this is just for your application question understanding, in case Cambridge decides to pull a fast one. So let's say I tell you that you need to have 4n plus 2 pi electrons, where n can be any like integer, from like 1 to, I don't know, whatever it is, or like 0 to whatever. So let's have something like this, right? We know that benzene is aromatic because within the ring, it only has 6 pi electrons, so it's aromatic, correct? Will this ring... Okay, how many pi electrons do you think this heterocyclic ring has within the ring? So let's look at within the ring. How many like pi electrons do you think it has? We know that benzene has 6 because there's 3 double bonds in the ring. So how many do you guys think like this has? Why do you say 6? Doesn't the nitrogen have a lone pair? So why is it that you say 6? Because remember that the nitrogen also has a lone pair. It's just one double bond and one single bond, so it's just a lone pair available. So do you guys think it'll be 6 or 8? Okay, so JVD's initial answer was correct. So the reason why that happens is that what Cambridge would normally do for questions like this is they'll tell you that this heterocyclic ring, which is called pyridine by the way, is aromatic. And then they give you some context like, oh, 4n plus 2 pi electrons is like the requirement for being aromatic. It's not because the lone pair can't be counted as pi electrons. It's back to like XJJ's point of, okay, it's sort of something to do with that. Basically, right, it has to do with the overlap of the orbital. And you're absolutely correct. If you draw the like your orbitals, right, for your nitrogen here, you notice that your pi electrons, right, or not your pi electrons, sorry, your electron pair, right, is sticking out of the plane. It's not in the same plane as the rest of the double bonds. Which is why even though this doesn't have like 4n plus 2 pi electrons in that sense, it's still aromatic because the lone pair can't be donated into the pi electron cloud. So it's just something to keep in mind in case Cambridge asks you something like this. Like it happens, you'll probably have like one or two like dumb questions like this in the paper. So it's just something to think about. Remember that in order for delocalization to occur, you need to have an overlap of the orbitals. That's a very important thing to keep in mind. So this is like a cool example, I guess. So yeah, NTUC, it's so okay. I can't. Okay, NTUC, like what specific reactions do you want to go through? Oh my gosh. Okay, yeah. Okay. Okay. The very organic sounding ones like the amino stuff. Amino stuff. Okay, let's go through what I think is a bit more difficult, okay? Oh, wait, we lost her. So is it because... Okay. I'll try and go through them. Alright, I'll just go through some directions and explain why you need to take off some of the things. So, let's talk about condensation reactions to form amides. So we know that in order to form an amide, right, what we have to normally use is an acid halide, which is a Cl, plus your whatever degree amine you want to use. So let's do something like this. And then you form an amide. So from this, right, you'll form a second degree amide. CH3, CONH, CH2, CH3 plus HCl. So remember I said just now about condensation reactions? Something's a condensation reaction if you have two molecules like reacting together to form a bigger molecule and releasing a small molecule like H2 or HCl. Now given that information, right? Okay. Do you guys think that this reaction can happen? Do you guys think that this condensation reaction can happen? Yes or no? Do you guys think that if I put a tertiary amine with like acid halide, that do you think there'll be a reaction if I do that? Just think about it for a second. No, like I asked if you guys think that a reaction is possible for the bottom set of reactants. Like, is it possible for an acid halide to react with a third degree amine? And why is that? Well, why can't I just kick out the alkyl group to form a RX molecule? Like, what's stopping me from just getting an RX molecule? Just think about it. Like, why can't I just form an RX molecule? Yeah, but like, why is it that I can't just remove like, why can't I just remove like an R group from the nitrogen and form like an RCl? Why does it have to be an hydrogen? Okay, the answer to that is in the reaction mechanism, but okay, there's two ways you can think about it. There's the more complicated way, which requires you to like Google the mechanism for this reaction or just look at the previous lecture that I did. Or you can think about it from the definition of a condensation reaction. So like I mentioned just now, right? For a condensation reaction, you only have like a small molecule fragment like leaving, so like a HCl or a H2O. And you see this trend being repeated many times in nitrogen compounds. For many of your reactions, right, you need the nitrogen to have a H that can be lost. I can't emphasize this enough. For a lot of the reactions, they only proceed if the nitrogen you're reacting with has something that it can stand to lose. So it can be a double bond for stuff that's outside of H2, or in this case, it will be a hydrogen. So just keep that in mind. Don't get scammed by something like this. And this can also, so that's something to keep in mind. And one more thing. What do you guys think are the conditions for this reaction? For the reaction, for the first reaction? In order for it to happen, what do you think the conditions need to be for the first reaction to take place? Think about, like, whenever you think about conditions, right? Let's say you forget an exam, like, oh no, I don't know what the conditions for this reaction are. Spend a bit of time thinking about temperature and stuff like, just think of like temperature and like what your reagents are. So let's say in the exam, right, you forget that, I guess, let's just say you forget that you don't know what the conditions for this reaction are. Let's say you don't know the conditions for it. Look at your reagents carefully. Your first reagent is an acid halide. Your acid halide. What do we know about acid halides? Like, what do we know about them generally? Like, what's one property of acid halides that make them very useful for condensation reactions? Very reactive, correct? And if you put something very reactive, right, that's formed from a carboxylic acid, what do you take note of? You can't put it in an aqueous medium, correct? Because if you put it in an aqueous medium with water molecules, what do you think will happen? Hydrolysis, correct? So what does that mean? It means our condition for this reaction is just reacting in an anhydrous medium. So that's just a tip for like thinking about the possible reagents. Think about your possible conditions. Think about what the type of reaction is, and like what your reagents are, like what do you have to take note of. It's the same thing for like, let's say you know your electromagnetic, your electrophilic aromatic substitution, right? And that's how they, whenever you use like those Lewis acid catalysts, you never put them in like aqueous like conditions, right? It's because those things will react super readily with water because they accept electron pairs very readily. And because of that, you have to keep in mind that, oh, we can't put these reagents in a like water, so it's an anhydrous medium. That's why you put like anhydrous like aluminium, AlCl3 for example. So does that make sense? And that's like a very useful tip. And for temperatures, right? You guys have to think about like what's going on. So like a very clear example of how you can predict the temperature of a reaction. Okay, this is a bit off topic, but I think it's very useful. Sometimes we go through it. So let's say let's say I have three things. I have this, I have this, and I have, oh gosh, that's bad. I have something like this. Now, what the heck is that? What on earth? Why did they draw a triangle there? That's so stupid. Delete. SMH. Okay, so let's just say our third one is like a COOH group on this. That's like your benzoic acid. Now, if I wanted to react these three things with bromine, what do you think the different conditions would be? Okay, not bromine, sorry, your NO2. Your NO2 plus electrophile. What do you think the different conditions for these three would be in terms of temperature? Okay, which one do you think will require the highest temperature? Just think about it. The third one, correct? Why? Because electron density is being pulled away from the ring, which causes your benzene ring to be less reactive. And because of that, the activation energy required for the reaction to happen is higher, so it increases the temperature. We also know that the second one has the lowest temperature required. In fact, you don't even need like aggressive conditions to do your nitration of your benzene ring for your phenol ring. And it's because your OH group, right, donates electron pairs into a ring, which increases its ability to like attack an electrophile, which makes it more reactive. So it needs to be at room temperature. So the best way to remember things, right, for reagents is to always compare it with something else. You don't actually have to remember everything, just have to remember one thing in particular. So we know that let's just say we know that your normal benzene ring it requires like 50 to 60 degrees, right? Like 55 to 60, was it like toluene or whatever? It requires like 55 to 60 degrees, right? If I compare it with something more reactive, like a phenol ring, we know that the temperature has to go down. So you can just get something like 25 degrees Celsius or room temperature. And let's say you use benzoic acid to react with for nitration. We know that because your benzene ring is less reactive when you put it with an electron withdrawing group, we need to increase the temperature. So maybe you can get something like 90 to 100. So that's one of the ways you can like save yourself if you forget the different conditions in reactants. And think about like just like your HNO3, like let's just see the formation of the electrophile, like NO2 plus. Do you think that you can form something like this if you have a lot of water sticking around? Do you think it would be possible to form an NO2 plus if there's a lot of water in your reaction mixture? What do you guys think? Do you think something as reactive as NO2 plus can survive with water molecules around? Exactly, it can't. Which is why whenever we want to form NO2 plus, we use conc H2SO4 and conc HNO3. Now, what conc acids are, right? It's basically saying that you don't have water. It's like acid in like the liquid form almost. So in that sense, because there's no water, your NO2 plus can survive. Because water is very good at reacting with positive charges. Like if this reacted with water, you just form back HNO3. So you can't have water basically. That's something to keep in mind. So that's like how you build up your knowledge of conditions and stuff over time. Was it useful for you guys, like the explanation on how to memorize like some of your conditions? Does that help? Nice, that's good. So like NTC, does that like help you out with like your nitrogen compounds in general? So just remember, like organic chemistry, right, is basically solving a big puzzle. You have to look at the puzzle pieces you're given and think about what some things are that you need to like keep in mind. So like, based on the information that we've been going through about like our benzene rings and stuff like that, right? If I told you, if you know that phenol, for example, let's say you forget about like your reactivity of your phenylamine with like Br2, for example, like the electrophilic addition substitute, like your EAS for Br. Let's say you remember that phenol can react with Br2 at room temperature. This is true, by the way. Like phenol does react with Br2 at room temperature to form your tribromo thing, which is a white PPT. Let's say you remember this. Now, given that you know that the mechanism for how your phenol works, right? If you forgot about phenylamine in the exam, what do you think would happen? Just based on the context of electron pair donations, what do you think would happen if I did this to like if I added aqueous bromine to like phenylamine? What do you think it would form? Like just based off your pure like basic knowledge for how benzene rings work. let's just say you completely forget about like, oh no, you just panic and think about, oh no, I don't know how this works. I forgot, I didn't memorize direction properly. Like, what would you do in such a scenario? Exactly. And NTC, why do we know that? Like, where does our knowledge of that, the fact that the multiple cell can occur, come from? We know it comes from the fact that about how these like groups attached to benzene work, right? We know that OH does that. It's activating because it can donate the lone pair, correct? And we also know that NH2 is a weaker base. Like we know that NH2 is a weaker base because the lone pair is donated into a benzene ring, and that's a huge clue about how it affects the benzene rings like reactivity. If you remember that our lone pair can be donated into a benzene ring, right? And which causes it to be less basic. At the same time, it also tells us that, oh wait, it works just like phenol. It means that if I wanted to react like aqueous bromine with it, it will react in the same way that phenol does. And once again form like your 2,4,6 tribromophenolamine with a white precipitate. So like what I'm trying to say, right? Okay, so this is like a larger picture, because let's face it this way. When you study your organic chem lecture notes, all the information I say for reactions will always be there. What's more important is you learn how to like condense and break down what is taught to you so that it's easier for you to remember and understand. Like I can't emphasize this fact enough, right? But the better you get at organic chemistry, the less you have to remember. And that's how you tell that you're getting better at organic chemistry. Because you understand how the reagents work. Try to like avoid just blanket memorizing. Like sure, you should memorize anyway just as a backup in case like I know your mind you have like a brain fart on the day of the paper. But always try to understand what's happening first. And then memorize. Because when you do that right, your memorization of your concepts are much stronger. Which is why also for your memorization part, I'm trying to make it more interesting by drawing mind maps or doing like table summaries, like I mentioned last lesson. That's what I keep in mind. So let's just move on with reaction commands a bit more. Like the main thing I want you guys to take away from this, like the value add, right, is understanding how organic chem works. It's like if you like think about stuff like this on your own in your free time, just compare a few molecules like within like the same like maybe like the same phenol ring and stuff, and just think about why different things react the way they do. Does it make sense? Like I really hope like the last 20 minutes taught you guys something useful. If not, that's gonna be extremely depressing. Does it make sense? Please tell me it does. Okay, that's great. Now let's ask ourselves another question. Going back to using prior knowledge and thinking about structures, why do let me ask you this. Why do 1 degree and 2 degree or secondary amides have a higher boiling point than third degree amides? This question tests multiple concepts at once. So think about it. Why do first and second degree amides have a higher boiling point than third degree amides? If you don't get answer right, draw the structures and compare them. Compare your structures of like the structure of a first like a primary amide to a tertiary amide, for example. And what's the difference? Hydrogen bond. Exactly. See what I mean? So like we know that for third degree amides, right, tertiary amides, right? There's no like hydrogens present. It's just alkyl chains, and because of that, the hydrogen bonding is no longer possible for that. So what I'm talking about, like let's just say I have something generic like this. So there you go. Versus this. Now over here you can see that hydrogen bonding can occur because there's hydrogens here. So what happens, right, if I were to draw it out, is that R C double one O and H H. This is how the hydrogen bonding will look. So the plus and H, double one O and R. So this is how the hydrogen bonding looks in case you guys didn't know. But anyway, like a lot of organic chemists, like if you ever get stuck in a question, right, don't just stare at it, draw the structures first. Because most of the time, like drawing out the structures can give you important clues about what's going on. It's the same thing for like why amides are less basic than pretty much everything else. In fact, amides, right? Okay. Do you guys think that amides are less basic than phenylamine or more basic? Less. Now, how is phenylamines basicity? Why are phenylamines like less basic than amines? It's because of delocalization, right? Correct. So when you think about like why amides would be less or more basic than phenylamines, you think about is the basicity of amides being affected by delocalization? And if it is, right? If the answer to the first question is it is, right? Why is it that the electron pair in an amide is more like the electron pair of nitrogen in an amide is more delocalized than that of phenylamine? That's the next question you have to ask yourself. So let's compare the basicity of this. Okay, Mr. Microsoft. Let's compare the basicity of these two things. So let's start off with our. Let's just compare this versus this. Now, most of the time, right, when you need to compare the extent of delocalization, you have to look at the different like resonance structures possible. So in this case, right, if I were to draw an electron into this, let's say I form a double bond, because it's being delocalized, I would have to push up this electron pair over here. So what's happening is that we form something like this instead. Now, the question you guys need to ask yourself, right, is that is oxygen good at stabilizing a negative charge? Like, is oxygen good at stabilizing a negative charge? We know that it's quite good at doing that, right? What that means is that our second resonance structure here is actually quite stable, so it's quite likely to exist. So what that means is that our electron pair, right, is actually like quite stable in this formation. They can stay here for that long. So our actual structure, like our actual resonance structure, would be something like this. So here, one here. And what this basically means, right, is that the electron pair is basically like delocalized into a thing quite well. It's like just delocalized quite well compared to something like a phenylamine. Where like I guess you can say that your carbon atoms aren't like holding onto a positive charge level if you draw the resonance structures. And that's like the actual structure of like an amide, like with the dotted bond. Because like your hypothetical like you see these two things, right? These are just like they don't actually exist. These two things are like they don't actually exist. What exists in real life, right, is something like a hybrid of those two structures, which is something like this. So this is what an amide will actually look like if you wanted to look at electron clouds. So always draw your molecule and just think about why the delocalization will be better in certain cases compared to others, for why something is more basic or less basic. Did that make sense? I feel like my explanation was a bit roundabout. But does it make sense? Okay. I'll probably just go through one more thing before I move on to the application question, because that one was like quite interesting. I think I should try it on. Now, given that amides would be rather unreactive, right? Because like, first of all, right, your carbon is less electron deficient because the lone pair is being donated, and on top of that, your nitrogen is less basic. So it just means that amides are very unreactive. And that's one more point I would bring up about general organic chem. You want to ask yourself why amides are unreactive, right? Think about what the reactive groups in amide are. So we know that if we just drew out like a normal amide, right, like forget the resonance structure for it, if we draw something like this, we would think that if something were to react with this, it would react at either the electron deficient carbon or the nitrogen lone pair, correct? That would be where like your first like thought goes to, right? Like, oh, if I want to react something like this, I would have to react it at either the C double bond O or like your NH2. You guys understand why? Like, does that like logical for you guys? Like thinking about why like the reactions for amides would theoretically take place at those two spots. Okay, right. So then, like, given that we know that if you wanted to theoretically react an amide, it will react to those two spots. When we're given the information that an amide is less reactive, the first thing we're going to do is we're going to analyze those two atoms in particular, right? The electron deficient carbon and the NH2 group. So let's think about that. In this case, we know that because the lone pair is delocalized into the high electron cloud, right? What does that mean? It means, first of all, that our carbon deficient atom is now less electron deficient. Correct? Do you guys understand why it's less electron deficient? Like just a few people, you guys can just type yes. Do you guys understand why a carbon will be less electron deficient if you delocalize the double, like an electron pair into it? What about the rest of you? I know JBD is good at chem, but yeah. What about the rest of you guys? Do you guys understand why it's less electron deficient? Well, let's explain like roughly. So when we want to talk about like whether something is electron rich, right, or electron deficient, we think about like the proximity of lone pairs to it, or if it even has a lone pair, or like any kind of electrons around it, basically. So when we have like C double bond O, right, in a vacuum, we know that because the electron pair is being pulled so close to the oxygen because of how electronegative it is, the carbon has less, like basically has less electron density around it. This is why it's like partially positive. You guys get that? So because of that, right, whenever we donate like a lone pair of electrons into that bond, like in the amide, what's happening is that the carbon now has more electrons around it, or more electron density around it compared to before. Yes, the nitrogen is technically more electronegative, but because the electron like pair is being donated, right, there's still some delocalization. So compared to before, the carbon still has a bit more like electron density, which causes it to be less electron deficient. And generally, right, your donation of lone pairs are a much stronger effect than your inductive effect. So your NH2 will affect the delta positive charge on the carbon much more than the CH2 group. You guys understand that? You guys get that? Around it compared to before. Which means that for stuff like nucleophilic substitution, it just can't like call onto its lone pair as easily anymore, which makes it less reactive. And that's why our amides can't undergo like nucleophilic addition reactions, and they can't undergo your nucleophilic subreactions. And now another question for you guys. You guys know the triiodide test? Like the one where you add like NaOH and I2 to like methyl ketones. Like, you know the test with I2 and NaOH, right? That test for like this group. Are you guys aware of that test? Do you guys know what I'm talking about when I mentioned that test? I just need to check. Either form, yeah. I find it quite triiodide. Either form, yeah, correct. Okay, I don't know why I called it. Okay, but anyway. Do you think that the either form test works with amides? What do you guys think? Like, I want more than one person answering this, please. Like, do you guys think that the either form test will work with amides? After all, right, this amide, let's say that this is a CH3 group. Do you think this group will give a positive either form test? What do you guys think? The answer is actually no. Amides and esters don't give a positive either form test. And that's because of how the either form test reaction works. So you know that the result, okay, let's think about this for a second. Whenever we like react like your methyl ketones, right? Let's just say we have like our group here and CH3. what is like the product, like what does this group turn into once we react to it and like for the iodoform test? Like what happens to the ketone? The CH2 group gets replaced with what? It gets replaced with something, right? You guys remember what it gets replaced with? O minus, right? Correct. So we know that it will form something like this. Now, in order for an O minus to get there, what do you think happens in the mechanism? Unless you know nothing about the mechanism, because it's not taught in H2, correct? But given that there's an O minus there, that means the O minus has to get there somehow, right? So how do you think the O minus would, like theoretically, right? If you had to think about this, how do you think the O minus would put itself there? Like what atom will it attack and stuff? Like what will react with what? Look at the reagents with I2 and NaOH. What do you think is happening in order for an O minus to get there? Yeah, so like let's just say like hypothetically it attacks a delta positive carbon. I'll say the actual reaction mechanism later in case it's wrong, but like let's say like from our understanding of chem, we assume that it has to do with something to do with like the OH minus attacking the delta positive carbon, right? Correct? And you remember we talked about just now about how the amides like see like the carbon has a less delta positive charge. So what does this tell us? It means that whenever we have an electron, like whenever we have like a group that's capable of delocalizing an electron pair, right, and our delta positive carbon is less electron deficient, it means that certain reactions that could happen before can no longer happen now. And that's exactly why the iodoform test doesn't work with amides. So this is what I mean. It can be really difficult to memorize everything at once. And if you're not sure, right, always like go back to thinking about how things work. Like go back to your fundamentals, because like walking through something like this in the exam, you can actually like see yourself like those extra 1 or 2 marks, and that can really matter. So do you guys understand how this works? Like, do you guys understand like how you can like sort of like think about this? Does this make sense? Like, do you guys get like how I would think through this like question if I forgot for that sense that amides don't react to give like the positive iodoform test? Like, do you guys understand this now? What about the rest of you guys? This is like almost the last thing. Like after this, I'm gonna go to the application question from one of the past A level papers, and then we'll call it a day. So just want to like check if you guys understand this. Okay, what about like some of the people that joined a bit later? Wait, NTC did get this first of all. I can't believe I'm like unironically calling someone NTUC. Interesting. Okay, but do you get what's happening here? Yeah, sure, I can repeat a bit. So I'll go back to like talking about this. So let's just draw this again. So normally, right, whenever we have an iodoform test that involves like a methyl ketone, for example, we know that the methyl ketone reacts with our reagents to give an O minus here. It replaces the CH2 group with an O minus. Correct? Okay, anyways, I'll speak a bit slow this time because I know I speak quite quickly when I get a bit more excited. So do you get until this part first? You get this part, right? Like that yeah, okay. So because there's an O minus being formed, right? It means that the molecule on the left somehow has to react with our reagents of I2 and NaOH to give us the O minus. Correct? So if you were to think about this, right, it means that some form of like nucleophilic addition or like substitution or something has to occur at the delta positive carbon. Right? You get that? That means that, let's just say hypothetically, the OH minus is attacking the delta positive carbon. So that means that for the reaction to proceed, there needs to be like a certain level of electron deficiency at the carbon. And we know that amides, right, make our delta positive carbon less electron deficient. So because of that, right, it's possible that the iodoform test is no longer possible with the amides because the carbon on the amide is less electron deficient, and the mechanism by which the iodoform test proceeds cannot occur anymore. Nice. And this is sort of true for many of the cases in organic chemistry. Like, a lot of mechanisms aren't gone through in H2, right? But if you think about it for a bit and you just Google, you can get it. And like Googling mechanisms and stuff, and we're just trying to figure them out on your own first, it's like, first of all, good practice for mechanism drawing. And it really solidifies your understanding of chem. Okay? Well, you guys can take a 5-minute break now before I go through one last application question, and that'll be the end of today. It's one more pass it over paper. Yeah. You guys can take a short break now. I'll be back at 11:35. Can you see the question? Can you see the question? Let's just make sure. This is like literally the most unfair question I've seen so far that's been said by Cambridge for an H2 paper. So, like, okay, how many of you are just like straight up confused when you first saw the question? When you first saw the question, like, how many of you just got like super confused when you saw this question? Like, this is like, this is like, if I saw this in A-level paper without like expecting something like this, I would be freaked out. So, what about you guys? Like, it's really difficult. Actually, does anyone have like any idea about how to proceed with this question, especially for like part two, like B part two? Like, it's a bit difficult, but like, okay, like it's not a bit difficult, it's very difficult. But let's just see like what you guys would do. Curious. This is the question where the knowledge of the circle fails. Try to calculate the concentration. Part A is okay. Part A is not the hard part. Part 2 is the very hard part. I'll go through both parts, don't worry. But okay, let's start with part 1. What do you guys think is the reason for why benzene is highly unstable? Let's start with that. Like, if you guys can do this question right, and then after you guys should give like a pen on your bags or something, because this is insanely hard. So let's just start with part 1. Okay, I'll draw a benzene first in case you guys don't know what it is. So benzene looks like looks like this. There's benzene. It looks very cursed, but that's what it looks like. Do you guys get that for the drawing of benzene? Yeah, because of the geometry. So first of all, we know that for benzene, the ideal like angle would be 120 degrees, correct? Like you want the sp2 hybridized carbons to be like at 120 degrees to each other, right? Because it's sp2. For sp2, the ideal angle is 120 degrees. But what's the ideal angle for something that's sp hybridized? Because we know that these two carbons, right, would be sp hybridized. So what would be the ideal angle for sp hybridized things? For sp3 is 109.5. For sp2 is 120. What is it for sp? Sp is linear. Just type out the angle in the chat. Like, what do you guys think it is for sp? Yeah, it says to be 180 degrees, but in this case it's forced to something that's less than 180 degrees. It's supposed to be 120. This is why it's highly unstable. The actual answer is like says that the carbon atoms in the C triple bond C are sp hybridized, and benzene with a bond angle of 120 degrees has a high angle strain, as the CCC, the carbon triple bond, is supposed to be linear with a bond angle of 180 degrees. So that's the answer. Now let's get to the more difficult part. Now, basically what the question is telling us is that our chlorobenzene is for conversion of... I don't think I missed... Oh, okay. There you go. Okay, so for this question, right, the premise is that we're converting our chlorobenzene to phenylamine with an NH2 minus electrophile. Now, right off the bat, right, why is this question so problematic? Just like straight off the bat. Like, what prior knowledge do we have about like phenyl rings that makes this question so hard to understand from our based on our prior knowledge? Like, what do you know about benzene? Like, generally, what do we just know about benzene? It's a nucleophile, correct? And we learned that in history that benzene rings can only react to form through electrophilic aromatic substitution, right? Now, what do you think this type of reaction is called? Like when nucleophile attacks benzene. if benzene attacking electrophiles electrophilic aromatic substitution, What do you think this is called? Correct. It's nucleophilic aromatic substitution. Now, let's think about that for a second. That's actually really cool if you think about it. And it's a legit class of reactions. And I really hate this question because it's not even a good example of a nucleophilic aromatic substitution. Because one of like the prior conditions is that you need electron withdrawing groups on the ring, but it is good with the flow anyway. Let's start off for the second part. So you know that the second part is just the real part of the question. We have to draw the structures and stuff. So it tells us that we're starting off with 4-chloromethylbenzene. That's our first premise. 4-chloromethylbenzene. So 1, 2, 3, 4. CO H3. And reacts with sodium amide, which is NaNH2, in liquid ammonia to give two isomers G and K. So G and K have the formula of C7H8N. Now, okay, so let's write down. Let's continue write the rest of the information. So we know that both compounds decolorize Br2 aqueous with the formation of white precipitates. That makes sense. And then compound J also reacts with Br2 aqueous to give a compound L, whereas compound K reacts with Br2 aqueous to give a compound M. So J to L, which has two Br atoms, Br subbed, and K to M, which has three Br subbed. Now let's go through this question in a systematic manner because it's something very new, right? We don't know what's going on. Let's look at the first part. First of all, we know that G and K have the molecular formula of C7H9N. What's the molecular formula of this? If you look at it, right, C7 H, wait, 1, 2, 3, 4, H7 Cl. Wait, that did come correctly. 4, 7. Oh my gosh, okay. I see why will come. Okay, C7H9N. Alright, so first of all, we know that that's the formula of our first like starting product, right? So the first thing to do is to see what's happening from our starting materials when it's being changed to G and K. So what's the change in the formula? Our Cl is being changed with an NH2, correct? Do you guys get that? Our chlorine is being replaced with an NH2 group. And we're given the premise that there is two groups being formed. We have like two isomers being formed, G and K. Okay? And we know that the product of J going through the electrophilic sub has two bromines, and the product of K being electrophilic sub has three bromines. Now, normally, what do we know about the substitution of bromine? Let's just look at phenol for a second. Normally, we have something like phenol, right? And we add bromine aqueous to it. We know that phenol is 2,4 directing, correct? We know that. Oh my gosh, okay, wait. We know that OH, like the OH group, is 2,4 directing, correct? So we know that you guys try substitute to form this. And we also know that our phenylamine does the same thing, right? Now, if we get two bromines being substituted instead of the expected three from phenylamines, what does that tell us? Like, let's look at the case of phenol. Let's say, like, when you think, like, we'll get, like, two bromines being substituted instead of three, what needs to happen? What do you guys think? Think about it. Correct, when a group is occupying one of the 2 or 4 positions. Right? So what does that tell us? It tells us that for J, right, one of the groups is occupying one of the 2 of the 4 positions. Now we know that the CH3 group isn't occupying 2 of the 4 positions, correct? So what does that mean? It means that the NH2 group is at one of those positions, correct? Do you guys get the deduction? That the NH2 group is occupying one of the 2 of the 4 positions, right? Do you guys get the deduction? that for J, the NH2 group is occupying either the 2 or the 4 position. Does that make sense? Just type like a yes in the chat if it does. Because it's very important, like, you have to do this step by step. So do you guys understand that? Okay, yes. Good. What about the rest of you? JBD and XJJ, do you guys get that? Or your NH2 group is occupying, okay, good. And XJJ, you guys do that? Okay, I'm gonna assume you get it, and let's just move on. Now, we know that in order for this to work, right, it goes through the benzyne intermediate. In this case, right, I'll just draw it out to like save you guys the misery of stupid computer. Okay, let's draw this out. So that's our thing. You know the CH2 group is here. This is why I hate how they do the circle. You see in this question, right, if that's a problem with only having the circle on benzene, but anyway, the triple bond will be there, and the other two bonds will be here. Okay, you guys get that? You guys get that will be intermediate for this reaction? Because we know in the first part we learned that the reaction proceeds via the benzyne intermediate, right? So you guys managed to get that intermediate. Does it make sense? By right you don't, but it really helps with understanding. You don't actually need to know the intermediate, but you guys like, at least get this part so far. Like, you don't actually understand, but like it's useful to know that this is intermediate. Because you see, right, the conclusion you eventually need to reach is that your final product for your G and L, right, one of the, like logically speaking, one of the nitrogens will be at this position for one of them, versus like the other one will be at this position. And the only way to explain that, right, to understand that, is to know that your NH2 minus can basically attack from this side or this side, which is why it occupies 2 positions. But you don't actually need to know this. If you can guess that you'll form those 2 compounds, it's good enough. But do you guys like get why there's like 2 possible? Do you guys get that there'll be 2 possible products? And do you guys manage to get those 2 products, like your NH2 at those 2 positions? I just need to check, like, you guys got those 2 positions, right? Okay, that's good. Now, once we get like these 2, right, we said to assign like our J and K to them, correct? Like we don't know which one's J, we don't know which one's K. Right? We only know that one of this is J and the other one is K. We just don't know which one's which. Right? Now, this is where the second trap occurs. I'm labeling the carbons are right? Okay. What do you think are the 2 and 4 positions? Which carbons are the 2 and 4 positions in this case? Just tell me, like, let's say 1, 2, 3, or 4. Like, which 2 are the 2 and 4 positions in this molecule for the one I labeled on the right? And which carbons do you think will be the 2 and 4 positions with respect to NH2? It's going to be carbon 3 and 4 because those are the 2 positions with respect to NH2. So that's the second trap in this question. It will be useful for later anyway. It's the same thing for NH2. Well, this one, right? This one over here. The 2 and 4 positions are this, this, and this. Do you guys get that? And what that means is basically that this can only have electrophilic addition substitution in this spot, so this has to be J. And this has to be K because this has 3 available locations. Do you guys get that? Like how to identify J and K? Does it make sense? Like, do you see which one's J and K? Yeah, nice. So given the information, right, let's draw L and M. So for L, we know L comes from J and it has 2 nucleophilic substitution two nucleophilic substitution positions. So what's nucleophilic? I mean electrophilic aromatic. Okay, I need more sleep. But anyway, NH2. Our two Brs will be here. You guys get that? And for one on the right, it's the same thing, but now we have a CH3 here, or NH2 here. So we can occupy the Br at this position, and this position. And that gives us M. Do you guys manage to get these two structures? For L and M? Hopefully it's relatively logical. Like so. Do you guys get this? Nice, that's really good. Like, if you can understand this, right? That's fantastic. You're in good stead for organic chem. It's actually really good. It's not exactly the key, but like if you do like think about the intermediate, right, it's a huge tip. It will help you a lot for understanding why there's two isomers. Like that really helps a lot, that's why. That's why like you think about it, right, for these type of guided questions, they won't give you some useless information in the earlier parts. Like since they're testing the same reaction that they mentioned in the first part, right, you have to understand that you have to use the information that they give over the benzene intermediate. It means that the information is important. Most of the time. Especially since it's the exact same reaction. But anyway, let's just do the last part of this question, which is what's the reaction from, what is it, J to K, J to L I mean. We like write the reaction equation. So, oh my gosh, okay, whatever. I'm so triggered at this automatic shape thingy. Makes me. Plus something becomes. Oh my gosh, we're almost done, thank God. Today was a long day and a long lesson. I'm sorry if my voice was quite dry, I guess. Okay, so fill in the two blanks. What do you think the two blanks are? Balanced, of course. Let's put the first reagent common the second reagent with the right stoichiometric coefficients. Since you got it, but just remember that there's two bromine atoms. Like since you got the second one correct, I'm assuming the first one was a mistake. Like since there's two HBr, there has to be two Br atoms, okay? But yeah, good job guys. This was like, you guys, like, I really hope this session helped you. It was a bit boring.